Okay, first I'll explain what a DFS tree is. Y'all can hear me, right?
Yeah.
Okay. So basically what a DFS tree is you have a graph. And then because graphs are normally hard to work with, like most of the time uh we don't want to work with the graph directly. So a useful thing to do with graphs is that you build the DFS tree. So like what the name implies, what DFS tree is basically you do DFS on it. So for example, if we have this graph, let's say we let this be the root. Then after that we do DFS on it. We go down, go down, and like in a DFS we keep going down until we cannot go down. Then we backtrack. Then after that oh wait, we can go down even more. Okay, this graph is not very good because it's just one line. But you can see that after we draw the graph like that, then I'll draw out the converted shape. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. Then okay, never mind, this is too messy. Let me redo this. Yeah, so basically what the DFS tree is that you do DFS on it. So this time I'll do in reverse. I draw the DFS tree first. Then after that I add additional edges. Yeah, so the blue edges are also part of the graph at first. But the interesting thing about the blue edges is that they are called back edges. So if you look at like the DFS tree, right, you realize that there are edges that are part of the tree. So for example, this one there are n vertices. Then there will be n minus 1 tree edges. Because a tree always has one less edge than the number of vertices. Then the back edge is just everything else. Everything else. Okay, and then interesting property about a back edge is that it always goes from bottom to top. So interesting property about a back edge is that let's say the back edge is from U to V. Is guaranteed that let's say U is the higher element, that V is in the subtree of U. At least for undirected graphs, we are working with undirected graphs here. Because for example, right, let's say that assume that in our DFS tree, right, like we say that this red edge is also a back edge. That means it's not a tree edge. But you can see that this is not possible because in our DFS, when we visit, we go here and then we visit this edge, then we visit this edge, then we visit this edge. Then you can see that here this vertex is not visited here, so the DFS will visit this first. So the red edge will become a tree edge instead. So like with this idea, right, we can actually observe that because you in a DFS you keep going down until you cannot go anymore. So the only edges that are not part of the tree is the edges that are already visited in the ancestor. So this property so this property will always hold because the only time that it goes, then the only time that it doesn't visit an edge is if it goes up. Otherwise, if it goes into the other subtree, then you'll continue to add on to the chain of the DFS. Does everyone understand this property of DFS tree? Are there any questions? This is the most important property of DFS trees, that the back edge will always go from an ancestor to a child, to a grandchild. If there are no questions, we can move on to the first question. So in the first question, what you need to do is either you are given a graph, you need to find either an independent set of exactly k over 2 vertices or a simple cycle of length at most k. So let's say we have a graph. Okay, so let's look at the condition of a cycle first. So let's say let's assume that we know how to find all how do I say this? So let's say finally, yeah. So let's say that we are able to find all cycles. So let's say that we know that all the possible cycles in the graph have length more than k, because they want to find a simple cycle of length at most k, right? That means they want a smaller than equals to k. But let's say that it's not possible to solve the second case. So if it's not possible to solve the second case, if case 2 is impossible, then this means that either there are no cycle, so which means it's a tree, or all cycles have length more than k. Okay, and then so if all cycles have length more than k, right, what this means is that if let's say that you have a cycle, let's say that all cycles have length more than k, then we choose the smallest possible cycle. So if a cycle is the smallest possible, it means that, like, let's say this is the smallest possible cycle, then this means that there cannot be edges in between, otherwise it will form a smaller cycle. So if we find the smallest possible cycle, it means that like all the edges outgoing from the vertices are like outside of the cycle. Like there won't be like uh other edges that goes in between the vertices in the cycle. So what that implies is that if we have a cycle of length more than k, right, if we take every other element, like you take one and then you don't take, and then you take one, then you don't take, then you take one, then you don't take, then those selected vertices will form a what do they call it? Will form an independent set of the cycle length divided by 2. Because we already said previously that there won't be an edge that goes in between the vertices in the cycle, which means that inside the cycle there are no other edges that goes in between the vertices. So if we like alternate, right, we take one, don't take one, take one, don't take one, then we won't ever take adjacent elements, so it will form an independent set. So since this is more than k, this means that the number of elements is k plus 1 over 2 floor, if I'm not wrong. If you have 3, then yes, and this is equals to k over 2 ceiling. So this means that if all cycles have length more than k, then we can always solve for case 1. Otherwise, we can solve for case 2. So now the only problem is, how do we determine whether case 2 is possible or not? So in order to do this, we use back edges. So what we do is that we do a DFS. Then we do a DFS, all of them are 3 edges, right? Until the first time we see that, there's one back edge. The moment there's one back edge, right, we stop and then we find what is the, like, let's say, we know that this is the first vertex that has a back edge. Then let's say that this vertex has multiple back edge as well. We choose the lowest one, which means that, like, if we choose the lowest one, is like the smallest possible cycle that we can make, like inside this DFS. So if we find the smallest possible cycle, then we just need to check whether it's smaller than equal to k. If it's smaller than equal to k, then we solve case 2 already. Otherwise, if more than k, then we can solve case 1. So basically what this task reduces to is to find a cycle that has no other edges in between them. In other words, we want to find a cycle such that the induced subgraph of the vertices in the cycle is the cycle itself. Like it's a graph where each vertex have a degree of 2. So we don't want to have other edges in between the cycle. We want to find the smallest possible cycle. Actually, it doesn't even need to be the smallest possible cycle. Like that, there can be, like, for this, like for this case, even if like there's a smaller cycle here, finding this cycle is also enough, as long as we can find a cycle such that there are no edges in between the other vertices, then we are good. Are there any questions? Okay, if there are no questions, I'll move on. Okay, so this question, it has like a very long and useless statement. So I'll just give a summary. What the task is basically asking for is that you have a graph and you want to pair up the edges. So let's say there are n vertices and m edges. You want to pair the edges up using like this kind of pattern. So you want to pair this edge with this edge. Like, you can pair the edges up if they share a common vertex. So like, if there's like a big graph, like for example, you can pair this edge with this edge because they share one common vertex. You can also pair this edge and this edge because they share one common vertex. Then you can also pair this edge and this edge because they share one common vertex. So you can pair them up however you want. So this is paired up, this is paired up, this is paired up. But what the question is asking for is they want you to make the most number of pairs. Each edge can only be part of one pair, so you cannot say like, oh, I want to pair this and this together also, because it's already part of the red pair, so it cannot be part of the blue pair also. So the task wants to ask you like, if we can pair it up in any way we want, what's the maximum number of pairs you can make? And then they also want you to construct the pairing. Yeah, so here 142 means that the edge 14 is paired with the edge 42, and then the edges are 14 and 42. Yeah, and then also got 43 and 32. Yeah, so as long as like the middle vertex is shared, as long as there's one common vertex, then you can pair up the edge. Okay, so normally for this kind of problem, right, for this kind of construction problems, the first thing you need to think of is, what is the upper bound? So for this one, the upper bound is quite obvious. Since there are m edges, each edge can only be part of one pair. So obviously, there can be at most m/2 pairs that you can make. And it turns out that this is actually always achievable. So in order to do this, once again, we use DFS tree. So uh, okay, so first, okay, wait, it's possible that it's not connected. So for now, we just assume it's connected, because if it's not connected, right, we can just solve for both cases individually. So in this case, it might not be always m/2. It's m/2 of one component plus m/2 of another component. Then you add both together, and that's the answer. But there's no point with the graph being not connected, so we'll just assume that it's connected for now. So after that, the way we solve this is that we do the DFS tree, right? And I think there might be multi-edges also. So first, we will handle the multi-edge. So if there are multi-edges, right, it's very easy to handle, because like let's say there are 3 of the same edge. Then we can just pair the 2 of them together, then we have 1 edge remaining. So whenever there are like k multi-edge, right, we can just pair the k/2 stuff together, then like the remaining, like there will only be k modulo 2 edge remaining. So either there's no more edge or there's only 1 edge remaining. So now we assume that there are no multi-edge. Okay, then the second part of the problem is that after you do the DFS tree, right, like there can be vertices with multiple back edge. Like you can see here, this vertex have 2 back edge, but this is also easy to handle. Like what we did earlier, if there are k back edge, then we just pair k/2 together, and then the remaining k modulo 2, which might be 0 or 1, that will be the only one remaining. So in this case, since there are two back edge here, we can just pair the both of them together, then remove this. So like the resultant graph, right, each vertex will have at most 1 back edge. Okay, now the final case, how do we handle the back edges? Okay, so we don't really have to handle the back edges yet. Like all we have to do is we consider the leaf. So we consider like the way we prioritize, like we want to push into a priority queue the depth of the leaf, and then first you want to sort by whether there's a back edge. So the first priority is you want to like the order that you want to visit the vertex is if there's a back edge, you want to visit it first. Otherwise, if there's no back edge, right, we want to visit the lowest depth first. So the reason why we want to do this is that, so let's consider a leaf that has a back edge. So for example, this, right? What we can do is that we can pair this edge with this edge. And then when they are both paired up, right, you can just delete both edges and then remove the leaf. So after you remove the leaf, right, it becomes a smaller graph with one fewer vertex. So it becomes an easier problem to solve. And then so whenever there's a back edge, right, we can always delete the leaf. Otherwise, if the leaf does not have a back edge, so let's say that we already handled the back edge, right? Like there might be back edges above, but we only consider the leaf first. So let's say that we look at this leaf. Then when you look at the leaf, right, you can once again pair up these two edges. So when you pair up these two edges, right, the entire bottom can be cut off. So now once again it becomes an easier problem. But again, there might be a case where there are multiple children. But in this case, it's so very easy to handle because we can just pair up the two children together. Then now we have a easier case where there are two fewer vertices again. So in either case, depending on whether its parent has no other children or its parents has multiple children, you can pair up with the other children or you can pair up with the parent. And then there's also the last case, which I drew here, that the parent has a back edge. If the parent has a back edge, then you can pair up the back edge with this edge. Then now you can once again remove the back edge and remove the vertex. So for this case as well, you reduce the number of vertex by 1. So now that we have covered all the cases, if we keep doing this until the tree has no more edges or only has one edge remaining, then the resultant number of pairings remain is m over 2, since like the only case that we break our while loop is when there's only one edge remaining, because when there are more than one edge, we can always do the same formula. So that's it. That's the solution. Are there any questions?
So I wanted to ask for the previous problem. We use the time of entry to see whether it has a back edge or
Wait, for question 1.
yeah, but also for this problem, you use time of entry to check whether it has a back edge, right?
For back edge, like you just time of, like normally how I implement back edge is just like normal DFS. Like it's just like I have a void DFS in U, right, and then in P, that's the parent, and then I do DFS. Then if V equals parent, then I just continue. Otherwise, if this V, right, then this means that we are currently at the back edge already. This is back edge. Then after I finish processing the back edge, I continue. Then otherwise I set this V equals to true. then I DFS VU. So this is how you find the back edge. So in the case of question 1, the moment you find a back edge, right, then you sort of want to push it into a stack first. Like you want to like stack dot push back V, because among all the back edge for this vertex, right, you want to find the lowest depth. Then it's only at the end, right, if not stack dot empty, then you want to like sort stack across, find the lowest depth among stack vertices, and after that immediately terminate like the entire program, because at this point you already found like the either the cycle of length k or the independent set of length k over 2. And then you also want to stop the DFS. So in a sense, like you sort of want to do this first, and then you use another for loop for this. So it's only if the stack is empty, then you continue to do the DFS. Yeah, so you do a separate DFS for that. Do you understand what I'm saying?
Yeah.
Are there other questions?
I have a question for the second problem. Do you
Okay.
need to use priority queue? Do we have to process the nodes with back edge first, or we just process the leaves in any order?
We have to process the leaves based on whether it has a back edge first. So if because you don't want a case where like just now I said, when you have the parent of the leaf, right, has multiple children, like you want to pair them up. But then you don't want the case where if you pair them up, right, then actually this leaf has a back edge, but you process this one first. So you can't really if you delete this edge, right, then actually it sort of works because the graph is still connected, but it's harder to handle because now you have to change from a back edge back into a tree edge. So to make it easier for implementation, right, what we do is we just process the leaf with the back edge first. And then the reason why we need to sort by the depth, right, is because, for example, you have a graph like this. Now if you process this leaf first, right, then you pair these two edges up. Then when you remove, right, you get two components. And the problem with getting two components is that it's not possible to solve in m/2 anymore. Because it's possible that if you break into two components, the answer is like the m/2 of this, m'/2 of this, and then the m'/2 for this. And the sum of this might not be equals to this. So like the property you want to keep is that every time you pair up and delete vertices, they still remain as one connected component, so that our claim that we can always solve in m/2 will hold by induction. If we break the chain, right, and then form two connected components, then we cannot use the induction claim anymore. So that's why we have to visit the lowest one first. Does that answer your question?
Yeah, thank you so much.
Okay. Are there other questions? Okay, if there are no other questions, let's move on to the third question. Okay, so this question is quite similar to the first question, but instead of like the just now, where we want to find a smaller than equal to k, right? This time we want to find a larger than square root n. So this time we want to find a bigger cycle. Otherwise, we want to find a independent set of exactly square root n. Okay, so the approach to this question is also back edges, but is slightly different. So for this case, right, let's say when we do DFS, and then we found a back edge that is very far away, more than square root n. If we found a back edge that is more than square root n above it, right, that means we already solved for case 2 where we want to find a simple cycle of at least length square root n. Actually, we can do more than equals. So if there are more than equals square root n vertices in within that's covered by this back edge, right, we already solved for case 2. So now the only case we need to handle is that if all the back edge, right, they only travel up to square root n. So all the back edge are like very close. They don't go more than square root n away. They are just like local, like very close changes. So the good thing about this is that because independent set, right, what an independent set is that you don't want like if you don't want to select two edges that like suddenly there's an edge in between. So what this means is that like you realize that if all the back edge are only close by, right, then those that are very far away, those that are more than square root n away, you can definitely take the far away one together with like sort of you can always take like in a gap of square root n because like there won't be a back edge that goes so far. So with this idea, right, what you do is that whenever you have a vertex, you check whether it's adjacent to any of the stuff inside independent set yet. If it's not adjacent, then you just add it. Then you continue down. This one is adjacent, so you cannot take. Then you go to the next one, you see whether it's adjacent. If it's not adjacent, then you continue taking. Then you just keep doing this procedure. So it's like a greedy algorithm. So this one got back edge, so cannot take. This one got back edge, so cannot take. So this one don't have back edge, so can take. So like even though this greedy algorithm might not be optimal, right, as long as there is no cycle of length smaller than equals to, as long as there's no cycle of more than equals to square root n, which means that all the back edge are smaller than equal to square root n away, we can actually prove that the greedy algorithm will find independent set of exactly of more than equals to square root n. So the reason why this is so is that each vertex, right, it can have at most square root n back edge, because whenever you have a vertex, a back edge must only go up. So each time there's one additional back edge, it will go one step further. So if the moment there are more than square root n back edge, right, that means it already taken more than square root n steps. So at this point, the cycle length is already more than square root n. But at the same time, if they are smaller than square root n back edge, right, this means that each vertex you choose will block only at most square root n vertices. So each time you take a vertex, if you block only square root n vertices, then you can do the same procedure at least square root n times, because each time you only block square root n vertices and then there are remaining n minus square root n vertices. So you can take one more, then it will be at least n minus 2 square root n vertices. So each time if you do it, you can do n minus n, which is n minus square root n square root n. So you can at least take square root n vertices before like the program terminates and it cannot find any more vertices. Okay, actually with this argument, I think our greedy algorithm might be a bit wrong. So because we are using back edge, so like what we did earlier with the leaves, right? This time we have to handle the leaf again. So since we say that each vertex that you take, right, it will only block square and vertices at the top. So once again, we look at the leaf. When we take the leaf, it will only block at most square and vertices on top. So whenever we take the leaf, we just remove it and then we continue processing like the thing above it. So if the thing above it is blocked, then you continue popping it. Only until you find a leaf that is not blocked, like you find a leaf that finally is not blocked by our previous independent set, then we can take it again. Yeah, so we have to use the leaf here because for any vertex in the middle, it might block the stuff above it also. So we cannot just start from the root. We have to look at the leaves first. So are there any questions? Am I clear?
If when we're going up and we don't find enough vertices, then when we have to and we get to the root, won't we have to combine some of the other paths so we'll get at least square root of n nodes independent sets, right?
Sorry, can you say that again?
Like when you start from the root and you go to one of the children,
Yeah.
and maybe on that path, it won't be enough to get square root of n, and maybe for every path of the children of the root, when we have to combine the children, so there will be at least square root of n nodes.
Like the way we do it is we process the leaf first. Like I realized my initial greedy algorithm starting from a root is wrong because there may be a case of a star graph. Then if you take the root first, it's instantly wrong. So the way we solve this is that we start from the leaf first. So since the leaf it has no edges at the bottom, all its edges are parents. All the edges are the back edge. And then since we said that there is smaller than square and back edges, right? So this means that whenever you take a vertex, you only block at most square and other vertex. So when you take this leaf, only the vertices that are directly connected to the leaf it will be blocked, which is the set of back edges that is connected to the leaf. Then after you process this leaf, you just remove it from the tree. So in this case, after you process the leaf, then you just delete it and then you move on to the next leaf or like any of these leaves. Then if each time you only block square n, so let's say at the start, right, we have a set S is equals to all possible vertices that can be added to the independent set. Then at the start, S is just the entire set of 1, 2, all the way to n, which is of size n. Then each time you take a vertex, it blocks at most square n vertex. So after one step, the size of the set is at least n minus square n. Then in general, after each step, right, each step will only block square n. So after k step, the size of S is more than equals to n minus k square n. So as long as the set S has positive size, we can always continue our algorithm. So the only time it's only after square root n step that size S can be possibly more than equals to 0 because n minus square root n. So we will always find at least square root n elements inside our independent set. Does that answer your question?
Yeah, thank you so much.
Are there other questions? Okay, if there are no questions, we'll move on to the last question, linear vertex cover. So for this question, basically what you want to find is a special kind of vertex cover. So a vertex cover is a set of vertices where each edge has at least one of its endpoint in the set, right? And then there's a problem called minimum vertex cover, which is a empty something problem, which is why it is not a problem here because it is hard to solve. Yeah, it is a NP hard problem. Yeah, so you can see here, like these two vertex is the minimum vertex cover because every single edge has one endpoint that is part of the vertex cover. So for this question, right, we want to find something called a linear vertex cover, but I don't know why it's called linear because it's a stricter version of vertex cover. And they only allow at most one edge to have both endpoints in it. So in our previous graph here, right, like this is a valid what is it called, linear vertex cover because only this edge here has both endpoints part of the vertex cover. But if you add another vertex here, like so for example, if you make the vertex cover even bigger, if you add this vertex also to be part of the vertex cover, then this won't be linear because both this edge and this edge have both endpoints inside the vertex cover. So this is not a linear vertex cover. Okay, so let us try to solve a simpler problem first. So for example, what if the vertex cover was even more strict? What if instead of at most one, they allow zero edge to have both endpoints in the set? So they allow zero edges to have both endpoint in set. So this means that even the graph just now, even this graph is bad because we want to have zero edges inside both sets. So the way to solve this is that you realize that since you want each edge to have exactly one endpoint inside the set, so if we have an edge, we want to have exactly one endpoint. So this has to be inside and this has to be not inside. Then you have a next edge, right? Then for this edge, right, since this one is already not inside, so this has to be inside. Then if you continue doing, right, you observe a pattern, right? This is bipartite coloring. So the only case that this can happen is if the graph is a bipartite graph. So this condition is equals to if the graph is bipartite. And then bipartite checking is very easy to do. You just start from the root, you label the root as 1, you go down to all the children, label as 0, then you continue the DFS. Then whenever you visit a back edge, you check whether the number on the back edge is the same as the number on both of both endpoints of the back edge, you check whether they are the same. If they are the same, that means it's not bipartite because like they have the same color. Otherwise, if they are different color, then you can continue. So if all the back edge have different color from like their endpoints have different color, if all the back edge have that property, then the graph is bipartite. But now the problem here is that the question allows for one edge, and most smaller equals to one edge. So if you think about it, right, it's roughly the same thing. So at most one of the edge, right, can have both ends inside. Then the rest will have the same pattern, will be bipartite. So basically what this means is that you can choose one edge and you just delete it. Like basically like the edge that has both endpoints inside the set is like a bad edge. So for the bad edge, you just straight up delete it. You just don't care about it at all. Then if once you delete an edge, right, and then you can color the remaining graph, right? Let's say there's like the entire graph here. If you delete the edge and the remaining graph is bipartite, then our problem is solvable. Otherwise, it's not solvable. Does anyone see why this is true? Does everyone understand why this is true? Are there any questions at this point? So the question reduces to, if you can remove one edge, is it possible to choose an edge to delete and the graph will become bipartite? Okay, if there are no questions, then I'll move on to explain how we can solve this. So once again, we construct a DFS tree. So let's say that this is a DFS tree. So we have two cases. Let's say we decide to delete a back edge. Let's say we delete this back edge. And then we use our same bipartite checking algorithm just now. We label them 1, 0, and then we only label using the three edges. So which is same as the algorithm just now. We just, when we go down an edge, we label 1, 0, 1, 0. Then for just now in our bipartite checking, we check whether the back edge has the same color, right? But then, so for this one, both edge have the same color. But for now, we don't terminate our algorithm first. We continue coloring because now it's possible that even though we don't have a bipartite coloring, maybe we can remove one edge and then it will still be bipartite. So we continue our coloring using the three edges first. Then after that, you observe that if you remove an edge, so you remove this edge, right? If you remove a back edge, the coloring remains the same because the coloring is only using the three edges. So this means that if you remove the three edge, the only thing that it changes is that if the three edge was a back edge, now it doesn't exist anymore, so it won't be bad. So this means that if after you do the DFS tree, right, if there's only one bad edge, which means that the both endpoints are the same color, right? If there's only one bad back edge, then we can just remove the back edge and the problem is solved. Otherwise, if there are multiple bad edges, right, then it's a bit tricky. So for this case, right, we need to start considering what happens if we remove a three edge. Okay, so for this case, right, let's say that we maintain a set of back edges that are bad. So I'll color 1 0 1 0 0. So let's say we have this back edge that's bad. Okay, we have how do I draw a nicer graph? Okay, let's say we have this back edge that's bad. We also have this back edge. We also have this back edge. Okay, now the idea behind this is that if we have back edges that are bad, let's say we remove a tree edge, so we remove this edge right here, then we can actually choose a random back edge to be a random back edge that connects the two components to be a tree edge. Let's say we choose this back edge. Then now when you choose this back edge, now instead of 1 this is 0, then instead of 0 this is 1, then now this is also 0, then now this is 0, this is 1, and then this is 1, and then this is 0, and then this is 1, and then this is 0, and this is 0. So if you choose to make a bad back edge into a tree edge, the entire subtree that of the tree edge that you delete, right, the entire subtree actually changes parity. So the nice thing about this is that all the bad back edge, right, that goes into this subtree also become good. Like you see now this 0 and 1 is good, this and then this 0 and 1 is also good. So the idea behind this is that we want to get the set of bad back edge, right? Then you want to take an edge that is part of all the bad back edge. So basically if you have like a bunch of back edges, right? Say the graph is something like that. So you want the back edge to be part of this chain, which is the first bad back edge, and also this chain, and also this chain. So if we are able to choose a tree edge that are part of every single one of the bad back edge, then when we delete that tree edge, right, then the parity of the entire subtree will flip, which means that these back edges will become good. But at the same time, right, we want to avoid the good back edges, right? Like for example, if we have a back edge like this. So since this edge is back edge is already good, right? If we choose to delete this tree edge, right, then it will change the good edge to become a bad edge. So we don't want that to happen. So this means that we want to choose an edge that is part of every bad. It is part of every bad back edge. It is part of every bad and is not in any good edge. Yeah, so this is the condition for it to be true. Yeah, so in order to solve this, there are a lot of ways we can do, like sort of prefix sums on trees to be able to determine like whether the edge is part of every single back edge, and also to make sure that none of the good edge is part of that edge. Yeah, then after that, if you can find the edge If we can find the three edge that satisfies both of the condition, then we can solve the problem. Are there any questions? If there are no questions, then that's it for today. Goodbye.
Goodbye.